All right, we're gonna go ahead and get started again. Again, sorry for the delay. No matter how long I make lunch break, we always seem to take a little bit more time. So we're going to start our next session, which is entitled Enter the Matrix, the Rise of AI. So this is the first time for PCC where we have a dedicated session towards anything with machine learning or AI or computer vision. Again, a dedicated session. We have had some of those kinds of talks before, but now we have 6 talks that I lumped all together. The first person who will be giving their talk is, I'm going to apologize for the mispronunciation potentially of your last name, Ara Nefian, who will be talking about crater detection for polar and equatorial lunar regions. So if you could go ahead and share your computer.
Yes, thank you, Stuart, for the intro. I'm sharing right now my screen. Yes. I hope you can all see it.
Yep, and we can hear you, and so I'm going to mute our room.
All right. Well, thank you very much, Stuart, for the introduction. My name is Ara Nefian. So the pronunciation was perfect. And today I'm going to talk about crater detection for polar and equatorial lunar regions. It's a method that we developed for performing a large-scale crater detection in a fully automated way. And we from NAC images that works, as the title says, at both polar and equatorial regions, and I'm going to show some results today. It's able to detect craters as small as 4 meters in diameter, which is basically the resolution of NAC images about 4 pixels. And we think that this method can be useful to the community for detecting craters, analyzing them, learning, drawing scientific conclusions based on something that we can do very fast and at a large scale. I'm starting with showing some of the results that we obtained, and next slides will be about explaining our method. But I'm starting in a way a little bit unconventionally by showing the results first, hopefully capture your attention more, and then go into more technical details with aspects of computer vision and artificial intelligence. We tested our method on 2 regions, one that corresponds to Apollo 16 landing site, and one that corresponds to Viper landing site, the mission. I'm sure you all know about it. Came out of NASA Ames, got canceled, unfortunately. I am showing here results on a NAC image that is written on the bottom. It's M1103. I'm not going to read the whole image, but you have it here. And the left image shows an area that covers roughly 650 by 100 by 1650 meters. On the right side, we have 2 detailed images, 2 cropped images, sub-images, and these 2 cropped images hopefully show better the better level of detail how our algorithm works. I want to mention here that on the left side we have a larger image to give the sense of the scale, but in fact we process multiple full NAC images from the Apollo 16. This is even the left image that shows more coverage is just a subset of the or a cropped version of the image of an NAC image. Here I have a slide, an image that shows the crater detection for just one area that is roughly 600 by 600 meters for the South polar region of the moon. You can see it's it's automatically generated, so it has some craters that are missed. But we claim that with this method we can reliably do detection of craters down to 4 meter in diameter with a reasonable missed detections. And here it's another subset area. Hopefully this gives you more time to actually see the quality of the results. I'm now moving to Apollo 16 area, so switching to equatorial regions of the lunar surface. We have the same structure of the slide. On the left side, we have a cropped image that is roughly 660 by 1650 meters, corresponding to an ACK image that is mentioned on the bottom. And on the right side, we have two crops of these images to show into more detail the quality of the results. And then here, again, larger scale, not larger scale, but I mean the image, a detail of the image is shown in the previous slide, again, just to give an idea of the quality of the results. Two images with pretty strong variations in illumination. Okay, and then I'm moving now into describing the way our algorithm works to give an idea of the advantages, disadvantages compared to other methods, ability to compare to other methods, and then emphasize areas where we can further improve it. One aspect that is specific to our method is that we do not train one crater model to cover all the images. We have all the images, all the NAC images, let's say. Rather, we train a new set of craters for every NAC image at different illumination conditions. So since these images are so large in size, for memory efficiency and for parallelization, we split them in blocks, and then we do detection at the level of each block. Each block, to give an idea, it's about 600 by 400. It's not about, it's 600 by 400 pixels, which in NAC images translate to the same number of meters, 600 by 400 meters. Once the craters are trained for these specific illumination conditions, we run our detection algorithm on each of these blocks. Then these detections are merged together and passed to the next step, which is also probably interesting to discuss, is we align the detection in the images to an existing DEM. In doing so, we are able to align even better the location of the craters, because now we have a detection in image that is done using neural networks, and we enhance the accuracy of that crater detection by matching it to pre-existing DEM. So, and then results from all the NAC images are combined again, and we have to run it again to a clustering algorithm, since many of these NAC images are overlapping. In order to get rid of multiple detection over the same crater, we have to run a clustering algorithm, and then we pass it to the final alignment to the DEM. As you can see here, I mean, we can run the same method on a block of a NAC image, on a full NAC image, on a set of NAC images that are overlapping, our method generates results in the presence of DMs or just using NAC images. Of course, if we have a DM, we can get more interesting results, depth to diameter, by example, of the craters, and also a better alignment of the craters, because now we have two sources of information. In the next slides, I'll go one by one through all these blocks and show at the end some statistics. As I mentioned before, we don't want to train one single model for all the craters that are visible in all the NAC images. I mean, that would be rather impractical. We'll need to spend a lot of time in labeling craters, and due to strong variations in illumination, I expect also to end up with some false alarms, a rather large number of false alarms. Instead, we use three classes for detecting craters. One is craters, the other one is shadows. We have a lot of shadows, obviously, especially at the lunar poles. And what I call flat regions. It's not necessarily a region that is flat. I call it like this for the lack of a better term. It's basically a region that is not in shadow and doesn't have craters. It can have a certain slope, but doesn't have any sort of topographic features or shadows. So the interesting part here is that we labeled only 300 images. So we are able to detect in the order of for Viper region, by example, we detected around 350,000 craters. And the similar number was for Apollo 16 landing site. However, we only used only 300 labeled craters for this, but these craters are labeled in the DEM. So for every new NAC image on which we detect craters, we re-illuminate these craters using the lunar Lambertian model. So we don't really have to do this manual labeling for every new NAC image that we get. We just label once 300 DMs, craters in the DM. We re-illuminate them for any new NAC image that we have, and we train the algorithm, the neural network for that specific illumination conditions and run the detection. This solution allows us to remove the person from the labeling of the craters and have a method that is fully automated for a very large number of images. The four craters here basically show the same crater under four illumination conditions. So you see the appearance is very different, but it's still the same crater. For the shadows and the so-called flat regions, we use only 50 images. And the training set is enhanced by changing the intensity to simulate various albedo conditions for the craters and the so-called flat regions. Of course, shadows are shadows. They are unchanged. The images, before being sent to the training step, are resampled at a size of 32 by 32 pixels to keep the training time at reasonable amount. The model itself is a neural network with only 3 layers, so it's a very simple neural network. It's part of the advantage of this method. It has a very simple training set and a very simple model neural network. The input layer has 32 by 32 by 3 nodes. 32 by 32 correspond to the size of the patterns, the training patterns. As I said, they are 32 by 32 pixels. And the solution works for color images as well. So we have uh, the size is 3 times bigger because in case of color images, we can actually use the color information as well. It has a hidden layer of 521 nodes, and the output layer 3 nodes corresponding to the 3 classes, craters, shadows, and flat regions. For training, we use TensorFlow, which is commonly used for neural network training or even for deep learning. Detection, again, is done on blocks of 600 by 400. We are detecting craters in the range from 2 by 2 pixels to 100 by 150, 150 by 150 pixels. Once we detect for a crater to be a potential for a pattern to be a potential crater, it has to have the detection value to be above a given threshold and to be also bigger than the threshold, the value for the other 2 classes, for flat and shadows. We end up with, of course, with a lot of false alarms. We have multiple detection for the same crater that are eliminated using a clustering solution that uses as measure both similarity in position and scale. Finally, all the craters associated to the same cluster that have approximately the same location and the same scale are reduced to only one detection. In this way, we avoid multiple detection and a large number of false alarms. We're moving now to the next stage, aligning with the DM. So we so far we're able to, or we've shown how we are able to detect craters in single images, and now we want to align these detections with the DM. This brings us two advantages: better positioning of the crater and better scale of the crater, and also gives us statistics about the depth to diameter, finding the rims of the crater. We have two profiles here, the image on the left side. On the top, we have the profiles along the first and the second diagonal of the detected crater. Sometimes the crater is on a slope. In order to detect the rims and the center of the crater first, we get rid of the slope. The second image shows the same first diagonal and second diagonal profile of the crater, but this time with slope removed. We have a simple algorithm based on min max to detect the bottom of the crater and the two and the location of the rims along the two profiles. The method for now uses only two profiles. As an improvement, we want to go beyond that, to go to 4 or maybe 8 profiles to get more accurate results. So the dots here represent the center and the left and the location of the rims along the profile. And these same dots are shown on the third row and fourth row on the image itself and on the hill shaded DM. As you can see, they correspond roughly to the exact location of the crater and the crater rim. However, the image can be improved in case the original location is obtained through image processing is wrong, we can adapt its location, recompute the location of the crater rims and the center, and use this information to find the optimal location of the crater. In doing so, the optimization, we have an optimization function for which the cost function is the minimization of the elevation of the crater rims and crater center in the two profiles. And finally, I'm running a little bit out of time, I guess, but I'm going to go a bit faster. We have some results on depth to diameter for polar regions. You can see here for craters size 2 to 16 meters on the left side, 16 to 32 meters on the right side. We reach a peak at about 0.03 and 0.06, 0.05. And we also have results for 32 to 150 meters on the left side, where we reach a peak at about 0.08. And we also have a histogram that shows our results over all the craters that we detected in the range 2 to 150 meters, with a peak again around 0.06.
I'm just going to interject real quick. We're going to shift all of the times of the afternoon session back by 10 minutes. So you actually have another 8 before we're going to go to the next talk. So you're okay. Don't worry. I mean, unless you have like 50 more slides, in which case you should worry.
I see. I think I have only one more slide, but I went a bit faster. So, but maybe we have time for some questions. A few more minutes. And then finally, this is the last slide where we compare our results in terms of crater size to theoretical values. The computed scale is shown in blue. The theoretical numbers are in orange, and you can see that we follow the distribution of crater sizes pretty accurately. So we use these measures also from I think they bring scientific value for crater characterization on the South Pole, but we also use them as a measure of validating our results. We don't have a way to compute the false alarms and the correct detections on an area that has more than 350,000 craters. So we have to limit ourselves to do these statistics to have an understanding of the quality of our results. And finally, here is my thank you slide with my email address for hopefully if this presentation was interesting and you in your work are interested in detecting craters on a very large scale, I'd be very interested to talk to you. I'm finished a bit early, I guess, so we have time for a few more questions. Thank you very much for your attention.
Clapping in the room doesn't help unless it's unmuted, but thank you for the interesting talk and for kicking off our afternoon session. And the one clap emoji that came up from Daniel. So I did not see any questions on the Zoom. Oh, no, Jamie just asked one. I may have missed it, but was there a statistical test comparing the two distribution functions?
The two distribution functions compare the what distribution functions for crater depth to diameter, or
Jamie, if you want to unmute, go ahead and engage.
Can you hear me all right?
Yes.
Yes.
Okay. I am some speaking problems. So anyway, I think it was the last plot where you have the blue and the orange
Mhm.
curves.
Yes.
So comparison of excuse me, those two, did you test to see if they were statistically the same?
We didn't. The only test that we ran, it was actually displaying this curve. We have the computed in blue and theoretical in orange. Um, I think that might be also interesting to show this results on a linear scale. Uh, but that's the only comparison that we have between the two graphs at this moment.
Okay, I'm not quite sure I understood all of that, but you could consider one of the class of the Kolmogorov-Smirnov tests to
Mhm.
compare. Is that what you're talking about?
Actually, we didn't do this comparison. It's a very good point.
What's the sample size on all of that?
The sample size, so the total number is actually 350,000 craters, but out of them we got
Okay,
we got the total number of craters, but we got the statistics for I think around 50,000 craters.
okay, in that case, with sample size that large, you're going to find an exception probably, even when there isn't one. So I guess, did you look at any of the confusion matrix comparisons?
No, we didn't look at the confusion matrix. I mean, we don't have a labeled a ground truth data set.
Well,
Due to the size of the size of the problem. So one solution to this would be to look into a smaller area, count craters by hand, and build a confusion matrix from there, I guess.
what's the x-axis label? I can't read it.
It's the crater size. Yes,
Ah.
it's yes. I know why you cannot read it because it's actually not written well. Yeah. Yes.
Okay,
Yeah. It's a problem with the image. In fact. Yeah.
okay,
So we have the crater size and the cumulative count on the y-axis.
yeah,
So basically, we measure the crater density here.
okay. All right, thank you. I think there's some evaluation tests that can be made to, that can be applied here.
Yes. Yes. Absolutely. Absolutely. That's a very good point. We showed the results at the beginning just to give an idea on how the method works, but I agree that further analysis of the results would be very valuable and also will drive the progress as we evolve this method.
Mhm. Okay, thank you.
Thank you.
Right. If there are any questions in the room, we have time for a quick one. Okay, deep breaths, digesting lunch, or whatever meal you might have had in your time zone. Although Sasha asks, what is the average number of false positives and misses do you get using the AI?
Yes, that's a very good point, and we do not have this answer at this moment. The reason we don't have it is, again, as I mentioned before, the large scale of we detected 350,000 craters, and that number is close to what they expect for the area. Labeling by hand 350,000 craters would be a massive amount of work. The plan that we have at this moment is to label a smaller area, of course, and compare the results over a smaller area. Of course, I mean there'll be problems associated with the fact that it's not going to be the whole area; it's going to be just a smaller set of samples. But again, computing these numbers will bring a lot of value, and will also track the progress of the algorithm as we move forward.